Stuff you need to know for chemistry. Okay, which subatomic particle determines the nuclear charge of an ion or an atom? Of an atom. What tells you the charge on an atom?
The ion charge.
Okay. What particle? There's 3 particles. What are the 3 subatomic particles of an atom? Proton. Okay. Which one tells you its charge? It's the number of electrons that it has. If the number of electrons exactly matches the number of protons, what's its charge? So if you have the same number of protons and electrons, what's the charge? We call that a neutral atom. What's the charge? It's meant to be way easy. You're way overcomplicating it. If you have the same number of protons and the same number of electrons, what's the charge on the atom? 0. Okay? Then if you lose or gain electrons from your valence shell, then you're either a positive or a negative ion. That's what determines the charge. Okay? So number 2, if an element has an atomic number of 12, how many electrons, how many neutrons, how many protons does it have? So atomic number, what does that tell you on the periodic table? It's magnesium?
Yeah.
That's not what it asked. How many protons does it have?
12.
How many electrons does it have?
12.
How many neutrons? Don't say 12. You have to do some math to find the number of neutrons. Do you remember how?
You minus that from atomic mass.
Yeah, the number of protons from the atomic mass. Yes, basically it's atomic mass minus atomic number. Whatever's left, because electrons weigh almost nothing, whatever's left tells you how many neutrons. So how many neutrons does it have?
12.
Also has 12?
Yeah.
Oh, that's a nice coincidence. So let's get my periodic table up and running here too. There was mine. Okay, so yeah, 12. Hey, what if, I can close this, Mr. Dueck, I can close this. Okay, what if, for the same element, how many electrons, neutrons, and protons would an ion have? So what we said was, the row that you're in tells you how many electrons an ion will gain or lose. Okay? Everything in this row is very unstable because they have one more electron than they want. Everything wants to get back to the closest noble gas because these ones have full shells. The reason they're called noble gases is back in the old days, noble meant doesn't react. They don't react. We have found we can force them to react, but for the most part, we're going to say they don't react with anything. They are inert. So how many electrons would this guy lose? No. Okay. How many electrons on its outer shell does it have? Look up, look up, look up. 2. So it would lose 2. It would still have, by the way, the number of protons never changes. The only time the number of protons changes is in some kind of nuclear reaction where an atom is actually changing into something else, because the number of protons is what tells you what the element is. Any element with 13 protons, that's aluminum. Any element with 33 protons, that's arsenic. It may have different number of electrons. You can muck around with the neutrons if it's radioactive, but the number of protons tells you what element it is. So even if it's an ion, number of protons tells you what element it is. So this question said, how many protons would it have? Still 12. How many electrons would the ion have? It would lose 2 electrons, which is why it says 2 plus. It wants to become 2 positive. It would have 10 electrons. 2 inner and 8 in the full outer valence shell. Remember all this? Yes, 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 yes. And number of neutrons won't change as either. It's going to still be 12 unless we muck around with the radioactivity stuff, which is later. Good, 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 good?
Yeah.
Okay. It says, use a Bohr diagram to draw an atom of magnesium and an ion of magnesium. Remember the Bohr diagrams? The Bohr diagrams looked like sort of like these, except much more like this. Okay? There's a classic Bohr diagram. Here's a shortened version of a Bohr diagram. There's a different type of a diagram, but this is the standard one that we went with. Okay? I'm going to pause for a second. So remember, for a Bohr diagram, usually we wrote the number of protons and neutrons in the middle. and then you had 2 in the first shell. How can you remember that there's 2 in the first shell? It's not a coincidence that there's 1, 2 atoms in that first row, hydrogen and helium. Mr. Dueck, I see 3. No, hydrogen appears twice because it's kind of a weird one. We aren't quite sure whether we want to put it one away from helium, which it technically is, or in the first row, which it sort of is as well. Then how many atoms, how many elements are there in the second row? 1, 2, 3, 4, 5, 6, 7, 8. How many electrons can you fit in the second orbit? 8. Third orbit, 8. Then it goes kind of screwy, and we got these, it gets a little much more complicated. We've really oversimplified things, but we said, you know what, we're really going to only be dealing with the first 20, 25 or so elements anyways. Okay? I gotta remember where I am. So, number 4. 2 MgCl2s represents 2 molecules of magnesium chloride. How many atoms of magnesium, how many atoms of chlorine are present? 2 magnesiums, grand total. 4 chlorines. Okay? Why do you need that many? This is the crisscross rule. If you look at magnesium, what's the charge on magnesium? What's the ionic charge? 2 plus. What's chlorine? 1 minus. When you crisscross, it means you're going to need 2 chlorines and 1 magnesium to balance. Yes?
Yes.
How many valence shells are present in the outer shell of nitrogen? Let's just do that one. So nitrogen, start counting from here. Where is nitrogen? Right there. It's going to have 1, 2, 3, 4, 5 in its valence shell. How many electrons will sulfur have in its valence shell? 1, 2, 3, 4, 5, 6. The closer you are to the outside, the more unstable you are. So these ones really want to lose 1 electron. Okay, in real life they don't want anything. They're dead objects, but we're pretending that they can have feelings. They want to get rid of an electron. These ones here really want to rip off an electron. So these ones, this is what they used for nerve gas, by the way, mustard gas and toxic gas. Chlorine, if it spills on you, it's going to burn your skin. It's going to be ripping electrons from your skin because it desperately wants to. Okay? Lithium, it's going to rip electrons. It's going to pass electrons onto stuff. It reacts very, very well with water and hydrogen and flame and all that. Gonna make it?
Yeah, my eyes are sore.
Yeah, no kidding. Me too. If carbon has 4 valence electrons, how many would silicon have if it's in the same column as carbon? Also 4. Anything in the same column has the same number of valence electrons. What's the difference between an ionic bond and a covalent bond? Do you remember?
Isn't covalent on these 2 gases?
Okay. Ionic is metal and nonmetal. Metal, blue, or these guys, and nonmetal, orange. Covalent is nonmetal. That's one way to remember how you can recognize it in a formula. In terms of what's going on, in an ionic bond, what we're actually saying is this guy is giving one of his electrons to that guy so that, come back, Mr. Dueck, so that we're happy. In a covalent bond, they're sharing electrons, and these are actually stronger bonds because they haven't given an electron up. They're sharing, and they still want to hang on to their original electrons as well. How many electrons are there in an ion of S2 negative? So where's S? Right there. Normally, how many electrons are there? 16? But it's an ion. It's 2 negative. That means it's gained 2 electrons to end up over here. You know how many electrons it has? 18. How many protons? Still 16. That's what makes sulfur sulfur. How many neutrons? 32 minus 16. Also 16. Coming back a little bit? Yes. Good. It says, draw a Bohr diagram for the atomic molecule H2, for the diatomic molecule H2. I'm not going to. You're going to have to recognize a Bohr diagram, though. You have to be able to pick out from a choice, because multiple choice, they're not going to be asking you to draw. I realize I should ask you to draw because that's better teaching, but we're pressed for time here. Lewis diagrams. What did Lewis diagrams look like? So going way back here, Lewis diagrams looked like... All we did was we showed the element and we showed the outer shell. That's all we cared about. Didn't care about anything else, because that's really all you needed. If I give you the element name and you find it on the periodic table, you know how many protons it has. That's its atomic number. You know how many neutrons it has. That's mass minus atomic number. All you really are interested in is what the outer shell is, because that's where the action is going on. And if it's an ion, the outer shell will be full. If it's an atom, the outer shell will be whatever the valence shell is. Is that okay?
Yeah.
Back to here. You're really having a tough time, my friend. Sure you're going to make it?
Yeah.
Okay? If you need to stop, let me know. We'll stop, we'll blink, we'll take a break. Give formulas. Okay, so this is where we're going to start to do some. So number 13, I'm going to go back to tutorials. I'm going to go clip. It's going to think about things for a second. We're going to start to give formulas for some of the following. Okay? This is where we're going to start to use the crisscross rule and the all that stuff. Okay? Sodium bromide. Sodium, metal or non-metal?
Non-metal. I mean metal.
Metal. Bromide, metal or non-metal?
Non-metal.
So this is going to be ionic. Cool. Okay. We're going to go like this. Na, what's the charge on Na?
Positive 1.
So plus. We're going to go Br. What's the charge on Br? It is Br, yes? I'm going from memory. Yep.
Negative.
Crisscross. Oh, wonderfully, these crisscross nicely. That would just be that. Nice. B. Iron 3 chloride. Now, why do they have that 3 there? Go find iron, which is Fe. How many charges does it have on iron? How many valence charge? How many ionic charges can it have? Find Fe.
3.
Found it? Yeah. There's more than no.
Oh, it has 2.
Or has more than one, does it not?
Oh, yeah, it has
Okay.
2 charges.
Right. Here's iron. What can it have? 3 or
2.
That's why they had to tell us which one.
Okay.
I know it's 3. That's what those Roman numerals mean. Chloride. Cl.
Yeah.
Charge.
Negative.
Crisscross. Fe1 Cl3. That's the formula for iron 3 chloride. Right?
Yeah.
Does gold have a Roman numeral next to it as well?
Yeah.
How come? It's got more than one valence. It's got more than one charge. So gold is Au, is that right?
Yeah.
And they told me that I want to use that one. What are the other options for gold, by the way? Gold can be a charge of 1 or?
3.
Or? Is it 1 or 3?
Yeah.
Okay. Iodide. I remember using the ide rule. It's iodine, ide when you're doing ionic, right? That's also a 1, is it not?
Yep.
Yep. So this one's going to be quite nice. Gold. Iodide.
Mm-hmm.
D. Ammonium. That's not an element.
Let's see.
I think is it NH4? It's a polyatomic.
NH4, yeah.
Charge.
Positive.
Phosphate. That's not an phosphorus is an element. Phosphate.
PO4, 3 negative.
PO4 3 negative, like that?
Mm-hmm.
Okay, now when I crisscross then, it's going to be NH4, 3 of them. PO4, 1 of them, so I don't need to throw brackets or anything. But if there was more than one, I'd put the whole thing in brackets. Yes?
Yeah.
Coming back. E. Manganese, which I think is an element. Oh, manganese, what's the symbol for manganese? Is it M or Mg? Or Mn?
I think it's MN. Yeah.
I need a definite.
It's MN.
Mn, and it's multivalent.
Yeah, it's 3.
No, it's multivalent. Yes?
Yeah.
Which one do they want me to use? Look at the...
2.
2 positive?
Yeah.
Okay. And hydroxide. Not hydrogen, hydroxide. Polyatomic ion.
OH.
Crisscross. Looks like I'm going to need 1 and
Nothing. Oh, 2.
yes. Okay. Right.
Yeah.
Now we're going covalent. How can I tell this next one is covalent? What's the first element in F?
Chlorine,
Metal or non-metal?
non-metal,
What's the second element in F?
monofluoride, or fluorine,
Metal or non-metal?
non-metal.
And when you go covalent, then you use the prefixes. Okay? So I can actually get this kind of right from the equation. Here's what it's saying. 1 chlorine, 1 monofluoride. It's actually monochlorine, monofluoride, but just like in math, we don't put a 1 in front of the X. We don't put a mono in front of the first element if it's mono. What can you, G, read it to me.
Dinitrogen tetraoxide.
If I crisscross, that's what I would find, but I can get that right from the prefixes. Tetra was 4, and you do have the prefixes on your formula sheet somewhere too as well, yes?
Yeah.
Coming back?
Yeah.
Good. This is so much fun. Let's keep going. Let's write the names for the following. So here now they're giving us the actual formula. Let me just hit pause for a second. So now we're going to write names. The reverse of this procedure. Now they're going to give us the formula, and they want us to go the other way. Yoink. What you have to do is identify ionic, covalent, ionic ide, unless it's a polyatomic, then just use the name. No. Covalent prefixes. So you ready? Look at that first one, 14A. Ionic or covalent?
Ionic,
How do you know?
because it's a metal.
What's Mg?
Magnesium,
It's going to be magnesium. What's I?
iodine,
But we use the died. There we go. As in somebody died.
iron,
Nope. Yes, but no. Here, how is iron different from magnesium if you look at the chart? Think valences, think valences, think valences. There's more than one type of iron, is there not?
yeah, iron.
So we're going to have to figure out by uncrisscrossing. We're going to have to go off into the margin here. We're going to have to say, okay, they said that uncrisscross, right?
Mhm.
Which iron?
Iron, Roman numeral 3.
Yes.
Oxide.
Oxide. Is gold multivalent?
Yep.
Uncrisscross. Can you uncrisscross in your head?
Mm-hmm. 1.
Ah.
Nitride. Ammonium.
Ammonium. What the heck is CO3?
Carbonate.
I don't know what that 2 is. I thought we put the thing in brackets with the 2 on the outside, but anyways. Next one.
Cesium, I think it is.
Look behind you. Cesium.
Okay.
Okay, fine. And if I hurt you, helium. Helium. Okay, fine.
Nitrate.
Nitrate.
Yeah.
And be careful, because there's a nitrate, a nitride, and a nitrite. And they all look very similar. F.
I think it's sulfide.
F. AU3. F. Not G.
Oh,
F.
Gold.
This is still ionic, yes? Gold what? Oh, you know what? F and C are the same one, aren't they?
Yeah.
That's not an element, that's a comment. G.
Sulfide or sulfur.
Okay, first of all, ionic or covalent?
Covalent.
How do you know?
2 nonmetals.
Okay, prefixes. How many sulfurs do you see in the formula? Meant to be really obvious.
1.
1, you could nah, we're just going to go sulfur. How many fluorines do you see?
6.
Hexa fluoride. Right?
Mm-hmm. So for covalent, you don't have to uncrisscross them.
No, because you do if it's, you would have to no, I'll just leave it at that. Yeah, the reason is the name comes for covalent, the prefixes come from the subscripts which you get after you've crisscrossed.
Okay.
Okay? H.
Nitrogen dioxide.
Okay. Yep.
Yep.
Okay. What if the nitrogen had a 3? Then it would be tri-nitrogen dioxide. That wouldn't balance, but I'm just making up. What if that sulfur in G had a 4? It would be tetrasulfur, whatever. It's just when there's 1, we omit the mono. Right?
Yep.
Cool. Let's keep going. What does the law of conservation of mass state? In a chemical reaction, the amount of mass before has to equal the amount of mass after. Doesn't go anywhere. And that was tougher to prove because gases, how do you weigh gases? It took, until we had the fancy schmancy instruments, it took scientists really, really, really sensitive, delicate measurements to prove, for example, that when you burn a piece of wood, the amount of mass doesn't change. If you collect all the smoke and all the carbon very, very, very carefully and you weigh that afterwards, it's exactly the same as the wood weighed before. That took a long time to prove. Number 16, list the names of the elements present and the total number of atoms for each of the reactants. What's the K?
Potassium.
How many potassiums are there?
2.
No,
Again.
sorry.
6.
There.
Okay. 6.
Okay. What's this? Now, I could treat that as a separate phosphorus, oxygen. No, actually, that's a polyatomic ion. What is PO4?
Phosphate.
How many?
2.
No. Only if... Yes, you're right, 2. I'm sorry, we don't need brackets. The brackets are implied. My bad. 2. Wow. Ammonium? 3 of them. What's SO4? It's sulfate or sulfide or sulfite.
Sulfate.
Sulfate? 2 of them. This is one of my beefs with chemistry, by the way. They love naming things obscurely. Why did you call it sulfate? Why wouldn't you have just called it, hey, how about sulfur tetraoxide? Because then I know exactly what it is, and you don't need to memorize a new name.
Yeah.
Right? Physics, we keep things simple. Got a hole, it's black, it's really big in space. Let's give it a name. Black hole. Upload Physics 12 review. I'm going to go sleep for 1 hour. A little reminder of something I need to do later. Got the sun. There's some spots on the sun. Let's give them a name. Sunspots. Anyways, there's my beef. Balancing equations. Okay. Here we go. I'm going to go one equation at a time. Now, on the provincial, what it's going to be is they're going to give you an equation and say which of these is balanced, but this is a good way to practice. Let's go like this. Dunk. Okay. I got chopped off a little bit, didn't I? That's a 2. All right. First thing we would have to check if they hadn't done already was make sure that they had crisscrossed correctly. They have, but if they hadn't, if they just gave me the elements and the reactants and figure them out, I would go Al, I think is a 3, F is a 1, and then when I crisscross, I would say, it is going to be Al, F, 3. Okay. How many aluminums?
1.
How many aluminums?
1.
You know what? That's not where I'm going to start. I'm going to start here and here. And what I'm really finding, I think, is an LCM. How many irons do I want on each side if I got 2 on one and 3 on the other? 6. 3 of those. 2 of those. Ooh, What did I just change by putting that 2 there, though?
Oh.
And we are now balanced, right? Dope. This opened in the background. Give me 1 second. All right, we're back. Clip. Let's try, ooh, B looks a little nastier. That bad boy. Excuse the 2 that's up there, just ignore it, right? This is, the crisscross is correct. The subscripts are in the right place. That would be something we'd have to worry about. Start. I think a good place to start is with the polyatomic ions, because if you get those right, that often dominoes taking care of the other ones. So the polyatomic ion that I see is PO4. How many PO4s do you see on the right-hand side?
4.
So I'm gonna need 4 of those. What just changed?
The potassium.
How many potassiums are there on the left-hand side?
12.
How many do I need on the right-hand side?
12.
What just changed?
The chlorine.
How many chlorines do I have on the right-hand side? 12. So you know what? I need 3, because that's a 4 there. That's supposed to be a subscript. Sorry about that. So I have 12 chlorines, 12. Ooh, and I noticed I had 3 leads, but I now have 3 lead. That took care of itself. I think we are balanced. Right?
Yeah.
Let's skip to one of the nastier ones. I thought that was pretty nasty. No, let's try D. Now there is a polyatomic ion, see it right there? But this is actually an acid-base reaction. And the reason I can tell is that OH is getting broken up into, oh, what's one of your products? Water. And so this is an acid-base neutralization reaction. This is the acid. Acids begin with hydrogen. It's hydrochloric acid. This is a base. This is calcium hydroxide. So for these ones, we said deal with oxygen and hydrogen last, because you're kind of hoping that if you take care of the other ones, they'll fall into place. So let's start with the calciums. How many calciums on the left-hand side?
1.
How many on the right-hand side?
1.
Meh. Let's try the chlorines. How many chlorines on the left-hand side?
1.
How many on the right-hand side?
2.
Okay, so let's try doing this. Ooh, what just changed?
The hydrogen.
How many hydrogens do I have on the left-hand side now? Count carefully.
4.
How many do I have on the right-hand side?
2.
Yes?
Mm-hmm.
Ooh, how many oxygens did I just pick up on the right-hand side?
2.
How many do I have on the left-hand side? Count carefully.
2.
Ah, am I balanced? Let's see. How many? Now, remember what I taught you was we actually made lists, right? We're moving a bit beyond that, you and I, today. But how many calciums? 1, 1, 2, 2, 2, 4, 2, 4, 2, 2. We're balanced. Ta-da! Skeleton equations. Skeleton equations were just writing the non-balanced crisscross and then balance them. So let's try, sure, let's do B. The whole schmear. Yes?
Mm-hmm.
Woohoo! Zinc iodide. Help me out. Symbol for zinc?
I think it's Z.
Charge?
Oh, it's a ZN. It's charges 2.
So down here, I'll write the actual skeleton. It's going to be ZNI2 when I crisscross. Yes?
Yep.
Plus copper is Cu, and they told me the charge is going to be 1 nitrate. It's polyatomic. No, not nitride, nitrate. Polyatomic.
NO3.
NO3 negative 1.
Yeah.
Oh, they'll crisscross nicely, so it'll be Cu. I like to use brackets because it helps me spot the polyatomic. They're optional, but I'm going to put them in. Becomes zinc nitrate. You said zinc was 2. That was what? So it's going to be 1 zinc, NO3, 2 of those. Let me scroll down a bit. Plus copper 1 iodide. Oh, that's going to balance nicely. By the way, what kind of a reaction is this? It's a double replacement. Can you see the zinc and the copper are just swapping partners? Double replacement. What was a single replacement? When you had a pair and 1, and these guys swapped in the original state and place, right?
Mm-hmm.
And then there was other ones as well, and combustion was, I got to go look at those and review those too, because I can't remember them off the top of my head right now. I'll recognize them when I see them, though, and that's really what I'm doing on the provincial here. Now let's balance. I said start with the polyatomic. Right?
Yeah.
Oh. Right? Because I just added 2 coppers, not 2 coppers. Oh, that's kind of nice because that gives me 2 iodines, and I have 2 iodines on the left-hand side as well. And, oh, we're done. Woohoo! Wahoo! Yay! Ho-ho! Ha-hi! Kalu-kale. Okay. Let's try and ask you one. Let's assume that as we go further, they get a bit more challenging. Sodium plus fluorine, that's a wishy-washy one. That's going to be Na, which is a charge of 1. F. You know what? This is a, what do we call this reaction here? Do you remember? Was it? I think it was called just a combination reaction? Is that?
Yeah.
I think. You've convinced me to go check my notes. Classifying compounds, types of reactions. Section 6.1 notes. We had 6 types. We had synthesis, not combination. Synthesis, 2 or more react to combine. Decomposition. Then we had single replacement, double replacement, neutralization, acid-base, and combustion, which always involved a hydrocarbon and oxygen, and always had as your products carbon dioxide and water. The balancing was the tricky part because you had C's, O's, and H's everywhere. Right?
Yeah.
Coming back to you. So let's try, how about potassium chlorate becomes potassium chloride plus oxygen. So this looks like we have a partial decomposition, or an, anyways, let's go see. Click. This helping, I hope?
Yeah.
Staying awake?
Yeah.
You're helping other people as well, because I'll put this online and I'll let the kids know. Potassium. Okay. 1, yes?
Yeah.
Chlorate. Polyatomic.
CiO.
Cl.
ClO3.
Charge?
Negative.
Oh, so that balances. That's just going to be KClO3 becomes potassium chloride. That's going to be KCl, and that's a 1 and a 1, right? That one's a nice little reaction. Plus, why is that wrong?
Because it's
Mr. Hofbrinkel. I think we start with the oxygens, yes?
Yeah.
How many oxygens on the left? 3. How many on the right? 2. Help me out. How many? I think 6. So let's try, first of all, going 2 of those and 3 of those. That gives me 6 and 6. Oh, but that gives me how many potassiums on the left? Oh! I think we're done. Yeah?
Yeah.
Cool. Now it says classify them as synthesis. It's a tough word for me to say. She sells synthesis by the seashore. Synthesis, decomposition, single replacement, double replacement, or neutralization. So this one here was a this one here, this first one is a, that's a wonky one, because I got phosphate and I got magnesium. You know what? I think something got chopped off there. That doesn't work. Because do you see magnesium here?
Mm-hmm.
Do you see it on the right-hand side? And sulfate doesn't have magnesium, so that A is wonky. This one here is a double replacement. This one here, hydrogen chloride, HCl, barium hydroxide. Ooh, acid and a hydroxide. This is an acid base. Sodium and fluorine becomes sodium fluoride. That's a synthesis. Potassium chlorate becomes potassium chloride plus oxygen. I guess that's a decomposition. We broke out some of the oxygen. Is that all right?
Yeah.
Distinguish between an acid and a base. You need to know your pH little chart. Acids are on the pH chart in which direction?
More acidic.
Lower pH or higher pH? If you have a pH of 2, are you an acid or a base? Acid. If you have a pH of 9, are you an acid or a base? What's neutral? Why? Because it is. Again, if a mathematician, water. If a mathematician had made up that scale, you know what would be neutral? 0. And acids would be negative, and bases would be positive, and that would make way more sense. But because they wanted to define it in terms of the power of high, anyways. Can you be more acid than 0? You actually can, but for Science 10, we're going to pretend not. Did I show you guys the world's most powerful acid? No, you know what? I made a note to add it to my lesson next year because I got curious, and holy smokes, there's pHs way, like, holy, don't even come close to touching those. It'll zip right through you. Okay? So state which of the following are acids, bases, or neutrals. Bleach, don't have to memorize it, right from the chart. Go find bleach. It's on there somewhere, yes?
Base.
Bleach is a base. Baking soda.
Base.
Water.
Neutral.
Lemon. Acid. Okay? We did pH. What color is bromothymol blue in an acid? You don't need to memorize that.
Yellow.
Yellow. What about on a base? I'm going to hope blue, because I'm guessing that's why they call it bromothymol blue.
Yeah.
Okay? What color is litmus in an acid solution?
Red.
Okay? What's the color of phenolphthalein in a solution that has a pH of 8? Now that might be a bit trickier. Let me get my color chart.
It's kind of pinkish.
Phenolphthalein, right at 8. So here's 7, right?
Yeah.
8, I think still colorless. I think just when you start to get to the right of 8, then it starts to become pink. I think. So you're okay on those, and you can translate those. A solution has a pH of 5, and solution B has a pH of 8. Which is more acid, and how many times more acidic? pH of 5 is more acid. How many times? Not 3 times, 10 to the 3. 1,000 times. It's a logarithmic scale. Richter scales work the same way. Identify the following as an acid or a base. Base, acid, acid, base. How did I do it so fast? What do acids begin with? No. What do acids begin with? Acid, acid. What do acids begin with? Hydrogen. Now, we need a dumb way to remember that. What letter does acid begin with? First letter of the alphabet, first element on the periodic table. I don't know, I just came up with that now. I couldn't think of anything when I taught this stupid lesson. Now I just came up with that, but better late than never, right? Base. What makes a base? It ends in hydroxide, OH. Those are bases. That's a, no pun intended, basic rule for bases and acids. Give an example of a neutralization reaction. So it's acid plus base, and then you end up with water, and the front part of the base joins with the back part of the acid. Okay, that's a neutralization reaction. So complete and balance, I think that's what we need a bit of practice with still. Yes, balancing equations. So let's do that. Yoink. What's the product going to be? Well, the Na is going to combine with the PO4, and there's going to be H2O, but I need to crisscross this properly. What's the charge on Na? 1, I got that one memorized, right? What's the charge on PO4, which is, I think, phosphate? Please tell me it's also 1. That would be wonderfully convenient. 3. Okay, so when I crisscross that, now let's balance. I would start with the polyatomic ion. I got 1 on the left, I got 1 on the right. Meh. For these ones, because the water is tricky, the hydrogen and oxygen, because they've broken apart, I'll save those for last. I would move to sodium next. How many sodiums on the right-hand side? How many on the left-hand side? 3 now. Ooh, I just changed the number of hydrogens and oxygens. Let's look at oxygens a little bit first. How many oxygens are there?
3.
So let's see, can I put a 3 there? How many hydrogens are there? 3 here and 3 here for how many? 6. And, ooh, 6. Whew, there, that one wasn't too bad, actually. Is that okay? There's an acid-base neutralization reaction. Organic or inorganic? What made up organic molecules? Carbon, hydrogen, and oxygen. Organic, in fact, really has to have carbon, except it can't have carbon as a polyatomic molecule. This is carbonate. That's not organic. This one is. This is chiku. This is, in fact, that weird acid. This was vinegar. This is the only acid that doesn't begin with, but that's on your sheet. In fact, you know what? I think the whole acids beginning with H's, it has some basic acid, it has some sample acids. Does it not on the polyatomic page? Yeah. So names and formula of common acids, you don't need to memorize if you just notice that both of the all 3 of the acids, all 4 of the acids start with which letter?
Hydrogen.
H. You are going to have to remember that somehow a base ends in an OH. A hydroxide, actually, is what we're talking about. Okay. Oh, and acetic acid. This is vinegar. They wrote it this way, so it starts with an H. But we said often they write that one as chiku, which I think is this one right here. Okay. Organics have carbons, except for carbon dioxide and carbonate. What 4 factors can affect the rate of a chemical reaction? Remember the video we saw? Now the video did 5 factors because it split one up into 2. It used your hand. It talked about getting a date as its analogy. So we can do this really, really quickly. Types of reactions. I think that's going to be chemical reaction rates, Mr. Dueck. Here we go. Temperature. Hotter means faster because atoms move back and forth faster. Surface area. If you break it up into smaller pieces, there's more exposed atoms, so the reaction can happen faster. A good example is, it's why a sugar cube takes much longer to dissolve in coffee than a spoonful of sugar, right? Concentration, you know what? If you have more of it, it'll react faster. And then the presence of a catalyst, okay? Right?
Yeah.
You guys did pretty good on that test. So describe the effect. Temperature goes up, reaction goes up. Surface area goes up, reaction speed goes up. Temperature, surface area. Concentration goes up, reaction goes up. Catalyst speeds up the reaction, and if you have more catalyst, you'll speed up the reaction even more. Okay. Last little bit of chemistry, I think. What's an isotope? An isotope is when the number of neutrons in your most common element have been changed. So isotopes, we muck around with the number of neutrons. The protons stay the same because the protons are what define an element as what it is. Neutrons change. Okay. How many protons and neutrons are in the nuclei of the following isotopes? Magnesium 26. So now we got to go to our periodic table. Magnesium normally has a mass of what?
24.3.
But what does this one have a mass of? 26. It's picked up some extra neutrons. Because the protons can't change. How many? How many protons does it have? What's the atomic number of magnesium?
12.
So now it's got still 12 protons, but it's got 26, take away 12, 14 neutrons. Okay? Nitrogen 15. Oh, yeah, nitrogen 15. What's the normal mass of nitrogen?
14.
So it's picked up what?
1 electron.
Not electron.
1 proton.
No, proton can't change. 1 neutron. Electrons have so little mass, we don't care about it. Electrons change the charge. They change how they're going to react with chemicals. Isotopes are, you're mucking around with the nucleus, the neutrons in particular. Why can't you change the protons? Because if you take one away, it's no longer nitrogen. It's the element behind nitrogen, which is what? Right before nitrogen is, sorry? Carbon. Or if you added a proton, it's no longer nitrogen. Now it would be Cu, copper? Yeah. Okay. The number of protons determines what the element is. The number of electrons determines its valence, how it will react. The number of neutrons determines its isotope. So this would be nitrogen 15. Oh, so how many neutrons will it have? What's the mass of nitrogen?
Like here.
The atomic mass of nitrogen from your periodic table?
14.
So that's the atomic number, isn't it?
No, the atomic number for nitrogen is 7.
Oh, is 7?
Yeah.
Okay. This one has an atomic mass, look up, of 15. Normally it's, the number is 7. Normally it has 7. So this will have 8 neutrons instead of the normal 7 neutrons. I think I said that poorly, but you figured it out. Give the name and the nuclear symbol for each of the following. An element with 8 protons. This tells you the element. Go find element number 8.
Oxygen.
Now, how many neutrons?
10.
So I would call this oxygen dash 10. Okay? 26 protons.
Iron.
Iron 30. Iron dash 30. Okay. Classify each of the following as, oh, and the other way you could write it was like this. You could write the element. Up here you wrote the mass. Down here you wrote the number of protons, the atomic number. Subtracting gave you the number of neutrons. Okay. Classify each of the following as alpha, beta, or gamma decay. You look at this. What? Beta. And remember, beta is also electrons. Whoop, what, this one is also electrons. Gamma, you could, alpha, I said gamma. Alpha, which you could write with an alpha symbol, but it turned out it was actually just 2 helium nuclei. Also, notice in the equation, things balance. How much mass did you start out with?
201.
How much mass did you finish with?
201.
How many charges of protons did you start out with?
80.
How many did you end up with?
81.
No.
Oh, minus 1.
What do you have? Still 80. It balances. This is how you could fill in the gaps. For example, what's your mass here? 225. This better add to 225. What's your charge? 89. This better add to 89. If it's beta, it'll be a negative down there. Gamma, which was pure energy, gamma decay had no mass and no charge, but hideous damage. It says, provide the correct symbol for the particle or nucleus that correctly... Okay, so let's try that with number 38. Holy smokes, we are going to get through all of chemistry. I should do this with my class. Do you think they'd find this useful instead of going through the provincial? Would it be better to go through something like this?
Yeah, and then like physics.
Okay, I may do chemistry on Friday and you'll get a double dose.
Okay.
Okay, and then I'll try and fit physics. Monday is our mock. Physics Wednesday, Thursday morning. I don't know. Please provide the blah, 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 blah that correctly completes. I'm not going to copy the whole instructions. Okay? So what they're saying, what is NP? It's element number 93. Find it. Neptunium, I think?
Yep.
Yes. What comes right before Neptunium, by the way? What element?
Uranium.
What comes right after Neptunium?
Plutonium.
Yes, they're named after the planets. Uranus, Neptune, Pluto. But Pluto's no longer a planet. Yes, we screwed up the period. Anyways, so it has to it has to still have a total charge of 93. With a -1 there, this better be a 94. That's the element number. What's element number 94? That's why I asked you what comes after.
Plutonium.
Symbol?
Pu.
Oh, the symbol. Sorry. Thought you were making an insinuation. Okay. Oh, how much mass do I have to begin with?
239.
How much mass here?
0.
So this better weigh 239. Oh, how many neutrons does this particular isotope have? Subtract. Right? Because that bottom number is the protons, and there's the mass. And that's why these atoms are so unstable. They have so many neutrons. It's very easy to dislodge. This is why plutonium is so good in nuclear reactors. I can knock neutrons off, have those go plunging into other stuff, and create more reactions. How many neutrons does it have?
145.
So we would call this plutonium. How many?
145.
Plutonium 145. I'm sorry, plutonium-239. We go by the mass. Plutonium-239. Yeah. That makes more sense. The next one, what element number is that Nd?
60.
So what is element number 60? I don't know this one. It's at the bottom. It's in the lanthanides, in the very bottom, second bottom row.
Neodymium.
Oh, neodymium.
Yeah.
Oh, you know where you use neodymium? We'll pause the video. Okay, we're back. Nerd moment over. How much charge? Oh, and by the way, they're only asking you to find this missing section here, but I would have no problem giving you this and saying find that, or giving you this and saying find that as well, right? The whole idea is the numbers have to balance all the way across. So I got 144 mass. Got to be 100. Nah, geez, 140. Geez, Dueck. Right? 60. Right?
Yeah.
When you give off an alpha particle, you're giving out 2 protons. You are actually changing into a new element. They thought this was impossible until Marie Curie proved that actually elements change into other elements. Up until then, they thought the periodic table never changed. What element? 58.
Cerium.
Cerium? Are you cerium? Yes, you are. You can't be cerium! Yes, you are. Sorry, I'm into the physics jokes. I made up your final, your mock, and on every couple of pages I did put a science joke. I just had to. So, last one. Ooh, what kind of decay is this very, very last one? Gamma. Okay, so that's also what that star implies. What that means is, what it did lose, though, was some energy. Okay. With me so far?
Yeah.
Okay. Then we talked about half-life. Half-life is how long it takes for half to vanish. If we have 512 grams, what's left after 32 days? We're going to go in chunks of 8 days, and we're going to lose half of this every time. So you ready? Got the hiccups?
Yeah.
That's okay. It means you're going to stay awake better. So, how long is the half-life?
8 days.
So it's going to go like this. 8 days, 16 days, 24 days, 32 days, and then I'm going to stop. How many half-lives? Do you see it? So we're going to start out with 512. After 8 days, how much is left? How much is left? How much is left? How much is left? Coincidentally, after 32 days, there's 32 grams. That's, oh, the number of days and the number of grams are always... No, that's just a coincidence. Don't think that's something you can memorize. Right? Somebody at the door?
Yeah.
Are we nearly done?
Sorry to intrude, gentlemen.
That's okay. So we got a graph. Answer the next 3 questions. Okay. First of all, it says, what's the half-life? Now, you do have some half-lives on your formula sheet. Hey, let's go find some of the radioactive stuff. Hello, yoo-hoo. They give you a few. Some, I think they do. I thought they did. Oh, no. Yeah. Right here. Common isotope pairs chart. They tell you what they turn into, and there are some half-lives. So here it's saying, what's the half-life of uranium-235? I can get that from my formula sheet, but I can also get it from here. If you look, it's around, because this is when there's about 50% remaining. If I drop down, looks to be about 750. Okay? Officially, 710 million years. Oh, wrong button. What percentage remains after 1,420 years? Okay, let's copy this question, Mr. Dueck. Dunk. So we said from the data sheet, what was it, 710
Yeah.
million? How many half-lives is 1420 if your half-life, if one is 710? They picked these numbers on purpose. What's 710 times 2?
1420.
They picked these numbers. This is 2 half-lives. In other words, if we use the same trick as before, but instead of 8 days, it's going to be 710, 1420. We're starting off with 100%. After a half-life, what percent is left?
25%.
That's the answer to B. What about after 3 half-lives? Well, how many half-lives have we done? 1, 2. So, what's the answer to C? 12.5. Really? 12.5%. You really had to reach for a calculator? 25 divided by 2? Really? Oh, by the way, make sure you do bring a calculator to the science exam. Yes?
Yeah.
What are the differences between nuclear fission and fusion? You need to understand what the word fissure and what the word fuse means. Fuse means forced together. Fissure, a fissure is a crack between, a fissure in the earth is a crack in the earth. Fission is splitting apart. So in nuclear fission, you're splitting apart atoms into smaller elements further down on the periodic table and releasing a little bit of energy. In nuclear fusion, you're starting with small elements like helium and hydrogen. This is what goes on in the sun. And you're fusing them together to get elements further up in the periodic table, which and also giving off energy. For fusion to occur, though, you need lots of pressure and lots of heat, like on the inside of the sun. We can replicate it in the lab, but we can't do it in such a way to get more energy out. We hope to. That's probably the future. Nuclear fission, though, yeah, we can start a chain reaction. We watched the video of the ping pong ball where they dropped a couple down on the mouse traps and suddenly they all went everywhere. That's a great example of a chain reaction. You're ideally going to get one atom to send out 5 or 6 neutrons, which hopefully hits some more atoms, which send out 5 or 6 neutrons. It's more complicated than that, but the theory is pretty simple. Number 42, consider these particles taken together. What's the total mass number? So this is some kind of a nuclear fusion reaction. The total mass number is 92 plus 141 plus 3 neutrons. What is 92 plus 141 plus 3? Okay. What's the total atomic number? We're going to be apparently, this looks like we're what? Combining stuff. I guess this is suggesting that we're going to end up with whatever the heck, a 92?
Yeah.
What's element number 92?
forming.
Yeah, you know what? I don't think this is forming well, maybe this is enriching uranium. Maybe this is what they do. I don't know. I'm not quite sure what they're getting at, but I can tell you the total atomic number is you add those two together, and there's a 0 right there, so who cares? Let's go to 43. What's the, and this is it? Yeah, this is all of chemistry. I may do physics on Friday and just put this online and tell the kids to watch this. Would that be better? For you? Okay, we'll see. What's the indicated daughter nucleus? All right. Well, things got to balance. Oh, let's cut and paste, Mr. Dueck. So what's the indicated daughter nucleus? Things have to balance. So let's first of all do let's do the charges, the bottom row. On the left-hand side, what does the bottom row add to? It's meant to be really easy. 92. On the right-hand side, what must it add to then?
92.
I'm missing a 42. That tells me what element is created when this uranium splits. Element number 42.
Molybdenum.
Molybdenum.
Yeah.
Symbol, please. I know there's an M.
MO.
MO. Like that. Let's see if we can figure out its mass. How much mass do we have on the left-hand side, grand total? 236. So we better have 236. Remember, this counts for 3, so it's going to be 236 minus 3 minus 119. What's left?
114.
What is the mass according to the periodic table of molybdenum?
95.9.
This is not going to be very stable. It's got way too many neutrons. It's very radioactive. This is radioactive waste. What's the mass of SN tin, element number 50, on the periodic table that you have?
118.7.
118, so it's not terribly stable either, but not as bad as the other one. Okay. Oh, let's complete the following radioactive. Oh, there's a plus sign here. What's the indicated? I don't think there's supposed to be a plus sign there. I think that's good. Don't know why that's there. Complete the following radioactive decay question. So we have 99, 99. I know this has a mass of 0. 43 became 44. This must have been a -1. Must have been a beta particle. It's giving off electrons. And turns out, we talked about this, I think it also gives off a neutron. Basically, no, it gives off a positron. It's kind of obscure. Anyways, for what it's worth, you can see, though, an element has changed into a different element. Why? Because what determines the element is the atomic number, the number of protons. It gained a proton. What happened was a neutron turned into a proton and gave off an electron, which is why that neutron is now positively charged. What about this one? What does that star mean?
Gamma.
Let's prove it. Atomic number 95, 95. It's got to be a 0. 247, 247. Got to be a 0. What's the only one that's 0 and 0? Gamma. This is radioactive americium. You would not want to hang around this. This is what eventually causes your skin to blister and blah. Right? This is what you think of when you talk about radioactivity. That's really what we're talking about. C. Yes?
Yeah.
What is element 65?
Terbium.
Sorry? Terbium?
Yeah.
Symbol? T what?
TB.
TB? What's its mass?
160. Oh, like on here?
No, here.
162.
What is it on your chart?
158.
158? So this has 158 point what?
9.
It's got 4 extra neutrons. Probably still somewhat unstable. Talk me through it. D.
82 goes to 82, so it's 0.
Yep.
And 35 gain 1, so it's going to be +1.
Nope.
-1.
Yes. Right?
Yep.
Right? Sure? Good? Yep.
Yep.
There's chemistry. That helped?
Yeah,
I hope.
Yeah, that's good.
Okay. So you're suggesting that I put this online and do a physics review on Friday. Yeah, I can do that.
I just don't want to like if people need help with chemistry, I don't want to.
Well,